All right, so today we're going to talk a little bit about same origin policy. Same origin policy is kind of the whole security model that the browser and documents kind of live in. We're going to talk about attacking authentication and authorization functionality in applications. We're going to talk about cross-site request forgery. We'll go into web services and some of the attacks you can perform on web services. And then we'll finish off with cryptography. Encryption is something that interests me a lot, and I think that if you guys put some time into exploring crypto flaws in applications, that'll net you a lot of good bugs in the future. So, same origin policy and kind of why XSS is so kind of important to the security of our applications. The same origin policy basically defines that JavaScript executing in the context of one document cannot access content in another document. So unless, of course, the protocol, the hostname, and the port are all the same. So what this means basically, if you have JavaScript running on www.google.com, that JavaScript can in no way interact with any page elements on www.yahoo.com. If it were able to do that, there'd be a fundamental security breakdown between the two sites, and Google.com would then be able to steal stuff off Yahoo.com and vice versa. And what the protocol, the hostname, and the port make up is what's called an origin. So in the same origin policy, when a browser actually does a check to see if a document resides in the same origin as another document, we have a couple use case or examples here. So if we've loaded a document off example.com in the A directory, what do you think JavaScript running on example.com/b what would happen if it tried to request resources from it? Would it be possible to load that content from example.com/a?
Protocol hosting and port are all the same, so it should be able to do it, right?
Correct. So the outcome of that is true or is positive. So that document will be able to access content from that. How about content that's loaded on www.example.com? Will our original URL be able to access that content? Anybody want to take a guess?
I don't think it will be able to.
And why is that?
Host name is different.
Host name is different. That's correct. What about the third example? Exactly right. The protocol is different. And the last one? The port's different. So none of these pages will be able to, or the original URL, example.com/a, will not be able to access any content on those pages due to those three checks. However, IE doesn't always observe that port rule, depending on what it's trying to access and from where. So that's just something to kind of keep in mind. And little kind of subtleties and differences between browsers when it comes to doing same origin policy checks. That kind of is outlined in the Browser Security Handbook. You guys can do a Google search on that. It has some really good information. So, as developers have, over the years needed to pull in resources from other applications, and the Web 2.0 world, kind of putting together mashups and content or web applications that pull in content from all different areas. We found that we have a need for kind of extending these same origin policy restrictions. So the first area where cross-domain policies came about was in Flash. And then Silverlight and Java followed suit. So the cross-domain policy is something a server can serve from its domain. It basically permits other domains from accessing its content. Basically kind of a whitelist of domains that can load its content. And the same thing applies for JavaScript and the XML HTTP request API. And that's through a specification called cross-origin resource sharing. If XML HTTP request makes a request to another domain's resources, the browser won't actually let that request or that API retrieve its response data unless the server it's trying to access returns specific headers in the response that actually permit it by its origin. And that origin is the host, the protocol, the host, and the port from which that request originated. And that's something that's set by the browser. And as application developers, they can't do anything to kind of work around that. When creating cross.
Can you just give an example of the previous, just an example, just to make things a little more clear? Because
You want an example of
the previous one.
Okay, so you have so if you have XML, if you have content on one page, and you have some JavaScript, and you want to load, say you're sitting on pentest.cryptocity.net, and Dan wants to make an XML HTTP request to google.com. It won't be able to access the content from google.com unless Google actually allows it to.
Okay.
And that's the same origin policy restriction. And that's something that the cross-origin resource specification addresses by inserting new headers in the response that would permit Dan if they wanted to. Yeah, so if Google wanted to allow Dan to make XML HTTP requests to its site and allow its application to access its response content and data, it would have to specify in its response headers a specific header, and that's the access control allow origin header, and basically that would have to define pentest.cryptocity.net in its value. So one of the things that you can do in these cross-domain policies is you can actually specify wildcards, and what a wildcard pretty much does is extend your same origin policy to pretty much every site out there. So if, say Twitter.com was serving a cross-domain policy that permitted all domains, basically the next site you go on will be able to access content from Twitter.com without any restrictions. And that's kind of how cross-site scripting plays a big deal, is you're getting JavaScript to execute in another context that would otherwise be restricted by the same origin policy. Kind of give you guys an example of how this kind of works. I have a demo with Flash, and you'll see the actual cross-domain policy come into effect when I make requests for resources on other domains. So on this page, I'm logged into a URL, an application at www.pentestclass.org. Let me pull up the magnifier. Actually, you guys can all see that, right? No problem? All right. So basically, when I make a request to www.pentestclass.org from the browser, something that gets sent in it is my cookie and some other information. Basically, when the browser accesses that resource, it sends whatever credentials it has along with it. And basically, just what gets returned is the data that the page is serving. So I have a Flash applet that's loaded on swf.pentestclass.org, as well as one on swf.gdssecurity.net. If I actually go ahead and try and make a request from Flash for that what's it called? For this URL, for the pentestclass.org /profile. If I try to make a request for this URL from an applet loaded on swf.gdssecurity.net, the first thing Flash is going to actually do is it's going to request its cross-domain policy file. And you can see that it's just trying to request /crossdomain.xml. And the server will respond with a cross-domain policy if it has one. If it doesn't have one, Flash assumes that it doesn't want any other domain besides itself from loading its content. So swift.gdssecurity.net is not actually in our list of allowed domains. So what's actually going to happen is Flash raises a security error. This is basically a sandbox exception from the cross-domain policy, restricting us from accessing that response data, or actually making a request to the remote resource and being able to retrieve its data. However, if I do the same request from swift.pentestclass.org, which is in the allowed list of domains, Flash will actually permit it to request that resource, and on top of that, will actually let you have access to the body or the response content from that request. You can see response data, things like that. Any questions on that whole cross-domain policy communication? All right. So kind of this same origin policy is kind of why XSS is such a big deal, is we're able to actually inject JavaScript into these other contexts and bypass these same origin policy restrictions in users' browsers to basically execute whatever we want and get access to whatever we want. Another attack is called cross-site request forgery, or vulnerability, CSRF for short. Basically, what happens when application has cross-site request forgery vulnerability, so basically it doesn't verify that the request that it receives, that the server receives, was actually initiated by the user themselves. For example, when you click a link, or if you browse a website with images, your browser actually just naively submits requests for those resources without thinking. And the server kind of has no way of knowing, whether somebody is viewing something as an image or actually physically clicking on a link, unless they actually include kind of a one-time per user or per session token in like a request parameter that knows that, okay, I served this page to this user, they're now clicking this link, and they're sending that parameter back to me. So I know that they are actually requesting this content. How this is actually exploited? A lot of times, for example, in an application that's vulnerable to CSRF, we would have like a victim user, Dan, logs into his account at bank.com. While logged into bank.com, he's surfing Gmail or surfing Reddit. And in one of those websites basically, the HTML calls an image or tries to request an image, but instead of actually linking to an image or sourcing an image, it instead does something like bank.com transfer from account equals Dan to account equals Joe, and amount equals 100,000. Dan's browser, not knowing the difference between requesting an image and submitting a request for something else, actually sends a GET request for that image. And what happens is, on the back end, because there's no kind of verification that Dan made that request himself, Dan just unknowingly, sent Joe $100,000. So to kind of give you guys a better idea, because it's kind of hard to visualize in your head how this actually plays out without a demo. It's kind of confusing at times. A lot of people mix up XSS with cross-site request for you. We came up with a demo to better show this. So I have this application called Hack Me Casino. In this Hack Me Casino, we have an account Joe user. He logs in and is able to kind of use the application to do online gambling. He could do other things, view his chip count and play blackjack, roulette, or poker. But thinking in terms of CSRF, what are some functionality that an online casino gambling site you may want to kind of look into to see if you can exploit a CSRF vulnerability in? Anybody want to take a couple guesses? It's perfect. Kai in the back said transfer chips to another user. So if I want to steal somebody else's chips, how do I do that? Well, I'm glad you said that, because that's the exact example that we've kind of enumerated. So I've actually gone and had a look and found this type of functionality where I can actually transfer chips to another player. So I want to transfer, five chips to my buddy Andy. He's in desperate need of some chips. He's got a gambling habit that he's trying to break, but these 5 chips will, kind of hopefully get him there, get him big. So I'm going to send him 5 chips. But when I do that, I'm going to go ahead and also intercept the request and inspect what the request looks like. To see if maybe this functionality is actually vulnerable to CSRF, because it might not be. So I see that we're requesting a resource post. We're making a post request to account/transfer chips, and in our parameters we're sending transfer 5, so 5 chips to our buddy Andy Aces, and our action is transfer chips. Let me just go ahead and let that request happen. And if I refresh, actually I did it too late. Our previous chip count was actually 3,376, and we just lost 5, or we transferred 5 chips to your buddy Andy. So we're going to see if this is actually vulnerable to CSRF. So we're going to go ahead and send that post request to our repeater tool. Let me just clean out some of these headers, make things more cleaner. And instead of sending them 5 chips, we'll send them 15. We're feeling generous today. So remember, we have 3,371 chips. we're going to send over 15, and can't see that response, but all right, so just refresh this, and we just saw that we just our chip count went down 15, down to 3,356. So this is kind of a prime target for exploiting CSRF in. So having known this, I want to be a little, sneakier. I want more chips. 3,000 ain't enough for me. So I've already gone ahead and come up with a slick scheme, basically to entice users to give me their chips. And the perfect place to have done this was on the user forums. And basically, I kind of create a post that lures people into clicking my link to give them 20,000 free chips. And the URL I link to is this right here. This Hack Me Casino Deals. This page. Seems innocuous, right? Until we actually view the page source and see that we're actually sourcing an image that actually points to the account transfer, the transfer chips request, and basically telling it to transfer 500 chips to our user. So let me go ahead and log out of this application, because kind of the deal's in play. We just got to sit back and wait for the chips to rain in. So, some guy Bobby Blackjack on the forums, trying to figure out what all the fuss is about this new deal. He wants to log in, check it out. He's going to go ahead and log in. Bobby Blackjack. And sees, I got 7,400 chips. That's quite a bit, but I could use 20,000. I'm sure everyone can. So let me go check it out. He goes to the forums. Let's, all right, let me just check it out. All right, deal's probably done. No big deal. Whatever. I might leave a comment telling, Joe user that, your deal's dead. Whatever. I go back into my profile, and I do a refresh, and I'm astonished that I just lost a bunch of chips. I got 6,900 now instead of what I had before. So what happened? Other than we just got our chips all stolen. Flaws like this have affected lots of different sites. I think a recent one, a popular one at the time, was one of the Bitcoin trading sites. Was hacked in just this way. Bitcoins were being stolen just like this. So other places you can use CSRF vulnerabilities is to kind of chain other vulnerabilities. So if there's like administrative functionality that you can't access as your user, but you can entice somebody that does have access to that through a CSRF vulnerability, you may be able to exploit whatever you were wanting to do. Common area for this to happen is in kind of router administrative pages, kind of resetting DNS entries and things like that. And kind of the mitigation for CSRF is really simple. It's just including just kind of application or have the application embed user-specific, session-specific token as a parameter with the request that the user has to send. That way, an attacker won't be able to guess that value to exploit CSRF. So our next section is on kind of gaining and elevating our privileges through attacking authentication and authorization functions. Authentication, there's a couple things an application can kind of verify user identity on. Things like a password or passphrase, those things a user knows. Things like a security token or a secure ID, RSA secure ID, that's something that the user actually has. And the last thing is something that the user is or does, something like a fingerprint or a voice recognition scanner. Typically, in web applications, you're not going to come across fingerprint or voice recognition in application, but you definitely will come across them if you are kind of assessing hardware or other types of physical applications. Some common authentication methods, probably the most common that you're familiar with, that most sites these days utilize is form-based authentication. Basically, you have an application return HTML that has a form that allows you to input your username and password, and that gets posted to some server URL. The second one is HTTP authentication. This is where the server will respond with that HTTP 401 authorization response code, and that will prompt the server, the browser, to pop up a dialog that requests a username and password. The form-based is kind of preferred by developers just for usability and UI purposes. But it's important to know different authentication schemes that you're using or your application is using. For example, with basic authentication, when the browser pops up that dialog to request your username and password, it just concatenates your username and password with a colon, and then base64 encodes it and sends it in the authorization header with every request from then on to the website that asks for it. Interesting thing about basic authentication, base64 is not encrypted or is not encryption, so you might as well be sending your credentials in plain text unless you're authenticating over SSL. But the other thing to keep in mind is there might be other servers like intermediate proxies, or the server itself may be logging request headers for debugging purposes, and if it's recording those request headers, your credentials might get exposed in something like a server log. So, kind of break-in authentication, believe it or not, one of the more common ways of breaking into an application, and not just web applications, is just through brute force. Thing to keep in mind when you are testing authentication methods and you are brute forcing usernames and passwords, to be kind of wary of account lockouts. Typically, most apps lock out after 5, so don't go straight in, start testing, and then lock yourself out, and then you won't be able to test anymore after that. Another thing to keep in mind is kind of pay close attention to response contents. When kind of brute forcing usernames and passwords, that may leak details about whether a username exists, a username is valid, or a password is not valid for a particular user. So with that said, anybody want to take a guess what the difference is between these two lines of code, or these two methods?
There's a missing period and please try again. So if your user is wrong, it would be a period. If your password is wrong, it would be no period. It says please try again. Right,
and that's enough. So basically, there's a missing period if the user submitted an invalid password. So that's usually enough for an attacker to kind of know that all right, so we have a valid username. Now let's start brute forcing that account. Other ways of breaking authentication is predicting session tokens. So depending on your server, session tokens may be completely random. They may be incremented by numerical value. They may be timestamp based. It's important to actually analyze session tokens that your application sets to see if there's any kind of predictable pattern they could do that kind of lead to a session hijacking. Another way is through SQL injection. If your login form is vulnerable, we showed that on day one of exploiting SQL injection in a login form. When it comes to actually authentication, servers, a lot of applications allow like remember me type functionality, and what this usually does is it kind of sets expires attribute on the session cookie that's set. So basically what this allows you to do, if you have access to somebody's workstation, your friend's laptop, and you just open up a web browser and you just browse to Gmail, chances are they've probably hit remember me, so you just log into their account like that. It's a simple way to hack someone's account. And oftentimes if you hit back enough times in somebody's history, if they've logged in and then used the application then logged out at some point, if you hit back enough times, you may be able to actually expose a form resubmission to actually post credentials again, and you may be able to capture credentials that way. If you ever actually used an application, hit back, and the browser pops up a window, a little error that says, do you want to submit this again? That's basically how you would steal those credentials. There's more than just logging into an application. You also want to look at other things that are authentication related. Things like password resets, registration is a big one, as well as kind of like the logout and session management. When it comes to password resets, are you able to reset a user's password without knowing what their email address is or what their secret questions are? On a recent pen test, I was testing an application that actually sent the user's registered email address a password reset link. So I'm like, all right, I can't get control of their email. So I'm not really sure, what that reset link looks like. Funny enough, though, when I did a view source, developer ended up including that link with an HTML comment. So I just took that reset link, pasted it into the browser, and reset the user's password. And basically, from then on, I could reset anybody's password, knowing that the reset link is in the source. So if you remember from day one, Joe kind of finished off talking about testing methodology. When you go and actually review an application, you want to do a comprehensive crawl of all the functionality and pages that exist. After you've done this, you actually want to go back and re-request those resources, both authenticated and unauthenticated, to see which ones can be accessed without having credentials. So authorization, the difference between authentication and authorization. Authentication is just verifying a user's identity, whereas authorization is testing to make sure the user actually has access to call or request a particular resource. And kind of different authorization attacks that we can perform on applications. There's typically vertical privilege escalation, then there's horizontal privilege escalation. Vertical being an example of going from a user role to a more powerful user, like a super user or administrator. And the other one being horizontal, where as an application user, am I able to access another user's information? One vulnerability that leads to both horizontal and vertical privilege escalation pretty often is something we call parameter manipulation. This is also known as insecure direct object reference by OWASP. So in this example, we have some database record identifiers exposed as an account ID parameter in a URL. If those two resources aren't protected at that level, basically we could just flip through account IDs and get access to other people's accounts. Kind of give you guys an example. We also have a demo showing this. So this is an example from WebGoat. We have this kind of human resources application. We have a user called Tom. We're going to go ahead and log into it. And what Tom can do once he's logged in is he can select himself from a list and view his own profile. Let me just intercept this request so we know what it looks like. And when Tom requests to view his profile, a couple parameters that he sends with it is an employee ID and an action. And the action is view profile, and the employee ID is 105. You can assume his employee ID is 105. So let me just go ahead and forward this request and return the response back to the browser. So here we have a list of kind of his information. Interesting thing to note is his manager is manager number 106. So knowing his ID is 105, let's go ahead and try and replay that request. But instead, we'll intercept the request and modify the employee ID to 106. It's a simple change. And instead, we get Tom's manager, Jerry, and his information. And we can do the same, go on and on. So we can easily, we can do this forever until we run out of numbers, but we can just as easily automate this attack, script it out. Nice functionality in Burp, the proxy tool we use, is a little tool called Intruder. It's basically, I can send this same request to Intruder, specify what positions I want to attack, or what parameter values I want to kind of fuzz. And for payload, I'm just going to keep something simple like bunch of numbers and range it from 100 to 125. Do step one at a time. Make sure there's no fractions. And one thing I want to do that Intruder has functionality for is to search the responses of that intruder attack for a particular string. And I know in the response there's a string called first name. So I'm just going to search for this and see which responses contain the string in the response. Do that.
That's the wrong request.
Ooh.
That's the login request.
She submitted the wrong request to Intruder.
Yeah, he did the login. He wanted to view profile.
Right.
And then changed it to 105 as well.
So in this, once this runs, we can quickly see which are valid employee IDs and which aren't, just based on searching for that first name in the response. So we know that 101 through 112 are all valid user IDs. Everything else doesn't seem to be valid because there's no first name in the response.
And more importantly, records that user is not normally authorized for. Right? That's what we're demonstrating.
Right. So, if you remember when we were first viewing that functionality in the application, we only had the ability to view our own profile and nobody else's. However, we're abusing that through parameter manipulation to view other people's profiles. So another common authentication or authorization attack is just to enumerate what a higher privileged user can access. So, when we're crawling our application and we're crawling it under different users, say we have a user and an administrator, we can compare the site maps of the two and see which URLs weren't available to, or which URLs weren't seen by the user versus the admin. And basically, as a user, just go ahead and force browse to those URLs just by requesting them directly in the browser, and see if the application returns that page, and if you're not, and at that point, if you can actually execute any functionality on that page. A simple thing is, if you have an application, just try and request /admin or /manager. It's a common administrative interface directory that a lot of applications are deployed with. Web services. In your testing, and as applications get bigger and bigger, they tend to rely on a lot more data, and this data can come from different other servers or other databases. And a lot of times, the way application servers actually retrieve this information is through like back-end web service calls. A lot of times, these web services are implemented using SOAP, Simple Object Access Protocol, and this basically defines an API for which a client can make requests for particular resources on application servers that host these web services. The API is kind of defined in a web services definition language, or a WSDL. These two terms might be meaningless to you, but it's kind of all the same once you start looking at web services overall. If you're using an application, you might not see direct web service calls, but you might see references to them that an application will make. So when you're browsing, pay close attention to the actual requests that are made. Sometimes the client does make a web service call. Sometimes there's links to one. Common endpoints end in .asmx. These are .NET web services. Other ones are /access. This is the Apache Access web service. Once you identify those, try and access those URLs directly. Try appending WSDL to the end as a query parameter or .WSDL as an extension. If the WSDL is available, the web application server will actually return that document back to you. And that document basically defines how clients should interact with it. It tells somebody implementing a client what its request structures look like, what the response structures look like. There's a lot of good information here.
It's kind of gold mine, isn't it?
Yeah, it is a gold mine of information. Basically, it tells you everything you need to know on how to make calls to it. And lastly, just start invoking that web service. Simple thing to do is load up SOAP UI, point it at a WSDL. SOAP UI will recognize that as a WSDL and actually kind of generate requests for you that conform to that protocol format that it's expecting. And once you have that, basically all the other application vulnerabilities that we talked about before apply to web services as well. So things like SQL injection, authorization, authentication, pretty much everything is fair game for web services that normal applications have. Other attacks on web services is attacking the XML parser itself. A lot of these web services are XML based. If you're not using enough, actually I won't go there. Two attacks you can do on XML parsers. There's entity expansion attacks, which is basically a denial of service. You send a XML document that defines kind of recursive entities, and the XML parser tries to expand that and basically runs out of resources doing that. The other one is a neater attack. It's called XML external entity attack. Basically, it could lead from information disclosure to pretty much anything. Just use your imagination. So an example of an XML external entity attack, we have to first have an XML message, and in our XML, we have to define an XML entity in our document type definition, and then we have to reference that entity somewhere in our XML body. So here, I define an entity, x3, that points to Etsy password, and then I reference it later on in an element called E1. When the XML parser actually is parsing this message and it supports resolving entities, it will actually go and retrieve Etsy password and replace ampersand x3 semicolon with the contents of Etsy password. You can do the same for network resources as well. Some XML parsers support retrieving remote resources via just a simple HTTP URI. So there's a lot of things you could do. And just a demo, we have an actual XML web service that just parses an XML message and returns you the same. So I'm going to use curl on the command line. Hope everyone can see that. I'm going to make a request to URL that's hosting our XML service. Where our XML web service is only expecting post requests, so we're just going to go ahead and use curl just to send an XML message. But first, we're going to set a header of content type application XML. we're going to send a payload of an XML message. First, we're going to send, just say, just a simple XML message like this and see what happens. Alright, so it just sent us back what we sent it. So let's go ahead and define a document type definition, a DTD, with an entity defined, x3 system, and there's a file in my temporary directory called poly, and let me just go ahead and try and request that. I ran into a parsing error for some reason. It's actually not poly.txt, it's actually just poly. Let me go ahead and request that. And that file, if we just do cat temp poly, says hi from poly. We just do the same and instead replace temp poly with any resource that this application server can read and pull down an entire Etsy password file. Our last section is on cryptography, and it's applications that use encryption. People are quick to run away from crypto when they see it in an application. I don't like to think that way because crypto is used on our most sensitive information. So if an application is actually encrypting data, chances are that what it's encrypting is really sensitive, and if we're able to change it or be able to read that information, there's the potential for us to do damage is really high. Also, when you're testing an application, you may run into scenarios where different encoding schemes are used, things like base 64 or base 36. You may come across stuff that's just hex encoded. Don't be so quick to give up because it's usually sometimes it's not crypto at all. Sometimes it's just gzip compressed, and a header wasn't sent in the response that told the browser to ungzip it. Regardless of what it is, whatever binary gunk you're looking at, it's always worth investigating a little bit longer what you can do with it. So kind of the encryption, the attack on encryption we're going to talk about today is attacks on block ciphers that operate in ECB mode. This is often the default mode used by various languages that have a crypto API. It's the simplest to understand. In ECB mode, we have a message or string of text. When we operate in ECB mode, we actually split that message into blocks of a particular size. And the block length that we split on depends on the algorithm that we're implementing. Most often, we'll run into 8-byte and 16-byte blocks. Can anyone kind of guess as to why we're even talking about this? Why ECB might be, how ECB might be vulnerable based on how it encrypts data?
The string has repeating patterns, and yes, it has ABC, ABC. So yes,
It's excellent. So repeating patterns in plain text will result in repeating patterns in ciphertext. An excellent example of this is encrypting Tux the Penguin, this image of Tux the Penguin. Um, the image on the left, you can pretty much make out what it is on the right. I mean, it's not exact, but you can kind of see what the underlying message is. So if you have a string of A's in one plain text and a string of A's in another piece of plain text, they're both going to encrypt into the same value.
There also has to be padding and all that kind of stuff, because not everything is every message should be divisible. And,
We'll talk about padding in a little bit. So, how you go about finding flaws in encryption functionality or pieces of application functionality that rely on encryption to keep things secret. There's a method called stimulus response testing. So you send a request, analyze the response. When it comes to crypto, there's three things we want to know. We want to know whether we're working with a stream cipher or a block cipher. Stream ciphers will be, for the most part, easy to spot. They both are actually pretty easy to spot. Stream cipher, kind of linearly, as you add more data, the resulting ciphertext it produces is the same length. So as you add more, it grows in size. If you're working with a block cipher, your encrypted output will actually jump in size based on its block size. So it may jump in 8-byte or 16-byte increments for the most part. And the third thing you want to know is whether a block cipher is operating in ECB mode or not. So here we're submitting a single letter to an application or to an encryption function, and it returns a string of bytes. This is 8 bytes in length. So we already know one thing. It appears to be a block cipher that's 8 bytes operating on 8-byte block boundaries. Go ahead, send 2 A's. Again, same length. 3 A's, same length. Of course, the output is always changing the more we add to it, but it's not jumping in block size. If we submit 7 A's, it hasn't grown in size. Anyone want to take a guess what happens if we submit 8 A's? Does it add a block, or does it stay the same size? It adds a block. It adds a block. That's correct. Reason why it adds a block is that extra block is padding. Block ciphers have to operate on messages or plain text that's padded to a block size. However, if our input data actually lands on a block boundary, for example, 8 A's, we have to add an entire block of padding to it. And that's just defined by the padding scheme that it uses. And if we add 9 A's, again, we're still at 2 blocks now. However, anybody want to see what's happening here? Anybody notice anything?
The second block.
Yeah, so once we've added 9 A's, that second block is actually the same as our first block. And same goes for 10 A's. That second block is the same as we saw when we sent 2 A's. So knowing this property of ECB, we can perform an attack on applications that rely on this through something called ECB block swapping. And basically, this is where we take ciphered text and shuffle blocks around to change its meaning. We just got a demo for this as well. So I don't know if you guys just saw that, but we have a admin user of this application that we're going to want to exploit or escalate our privileges to later on. However, we first need a valid login because we don't know that admin's password. So we're going to go ahead and just kind of register for this. I'm just going to register user ID, Marcin W, and password Fubar. Go ahead and register. And I just noticed that one of the things I can do is edit a profile, and that's pretty much it. So let me go ahead and take a look and see what the server responded with when we actually did a registration and were able to log into the application as a user. So one of the things that the application set was a SID cookie and the session cookie. Having worked with this application before, I'll tell you the session cookie is not used by this application. Instead, it's a SID cookie. So we want to find out if that SID cookie is being encrypted with data that we can control. If it's data that we can't control, there's really we're kind of limited as to what we can do. There's still attacks that can be performed against it, but for our intents and purposes in this scenario, we actually want to just get admin log in as an admin. So I'm just going to fill out my profile here and just go ahead and say Marcin W, Marcin W, and just update that and see the SID cookie that gets returned. So what I sent is this right here, this value for a SID cookie. Let me just open up Notepad. We can track this in. And then what the server actually set was a new SID cookie. So if we take a look at these, we can actually see that we start repeating values right here. It appears like we have 3 blocks that repeat themselves, starting with 320, 320, and 320. So I'm going to assume that that's our information that we sent Marcin W, Marcin W, Marcin W. Doesn't appear like the password actually does anything there. So let me go ahead and change this. Let me change my last name to something like admin. See how that works. And if we compare our responses, or the SID cookie values that were returned, just so happen to be that that third block that was originally the same as the others is now different. So we're going to actually take this block and instead move it to the front. Just guessing. And resubmit this request. Let me turn on intercept and just request this again. This time changing my SID cookie, that. And we just got access to the admin panel just by shuffling blocks around in ciphertext that was encrypted using ECB mode. Yeah, what I did was I rearranged the blocks so that what I thought was being encrypted as my last name and moved that up to the front of my ciphertext. Password didn't matter because this application is actually decrypting that cookie and taking whatever value is specified as a username in that cookie and authenticating the user as that. So we just abused an authentication functionality of this application through attacking SID cookie that was encrypted using ECV mode.
I find a lot of apps in the wild that are that bad in terms of authentication.
So interesting you say that. Joe just left the room, but literally 3 weeks ago we came across one that did this exact same thing. I mean, basically how we ended up exploiting is we ended up registering multiple users and just kept adding A's until we found what block admin aligned on, moved that up to the front, authenticated, just had admin access to the entire application. So it does happen, and it happens a lot more than you think because crypto is pretty hard to get right. And oftentimes whenever we see encryption happening, oftentimes it's done wrong. And there's very subtle flaws that break in a spectacular way, such as this.
8 bytes seems like a really tiny block size, too. Are there many ciphers that use that block size?
Does
Well, that's
otherwise
modern
you
ciphers.
otherwise I mean AES would operate on a 16-byte block cipher, a 16-byte block boundary, but it's not much different.
Those are all really small. It seems like this would be mitigated really well if you used a larger block size.
No, because if you could just send more data into text you control. For example, if you were to set, if I was to go back, and set if I changed my last name to a bunch of A's, updating that, we just get longer ciphertext. Whether or not we're operating on an 8-byte or 16-byte block, adding more bytes to a block size is not going to address this issue. There's a couple different ways to address this. One is not using ECB mode, and two, using an HMAC to sign the ciphertext, and then validate that signature when you retrieve it back on the application server side. But a lot of times applications don't use HMACs to validate the integrity of the encrypted text that it's receiving. So he just asked if we've ever come across that, and just like 3 weeks ago.
Seems more than you think, actually.
Yeah. So
People use ECB mode because
it's oftentimes
easier.
the default.
So I didn't realize it.
And it is easier to use.
Yeah.
Other modes, for example, CBC require a unique IV. There's flaws in CBC mode as well that can be exploited, and we're going to leave that as an exercise to you guys to explore. There's plenty of research in the past couple of years exploiting various flaws in that. So going on to randomness and using random numbers in cryptography, random numbers is kind of vital to all our crypto operations. And if we don't have good randomness, we can't really rely on anything we do with it after. So two common attacks on random number generators is basically reconstructing RNG state from a sequence of output that an RNG produced. Second one is coming across a situation where the same RNG state is used twice to produce the same random number. For example, this kind of happens with the RSA compromise, where seeds were compromised for secure ID tokens. If at any point in time a seed is compromised that was used to seed a random number generator, an attacker is able to observe 2 or more outputs from that random number generator, they can then predict what every value that's returned by that random number generator from then on out. An example is if we create a random number generator here in Python and seed it with some value, and we observe some output. If you compromise what that seed value is, you can run up to this last one and figure out what the next return value will be. Another thing to keep in mind is applications that use random number generators. Statistically random is not the same thing as cryptographically random. Using an insecure random number generator is going to produce insecure results, while statistically random or mathematically random, some set of output may appear. It doesn't stand up to abuse and attack from a cryptographic sense. And if at any point in time you have control over any data that is being used to seed a random number generator, the output from that random number generator can't really be trusted either. A lot of times the various languages that have basically a random number generator and cryptographic random number generators, the differences between the two often lies on how they're seeded. The insecure versions basically rely on the system clock time to seed them. So this kind of leads to a scenario where if you can, especially like in an application, web application, if you could submit tens or hundreds of requests to the application at the same time, sooner or later, 2 or more of those requests will actually instantiate a random number generator that's been seeded with the same exact clock time as the other. And the output that those 2 random number generators will return are going to be the exact same. This becomes especially critical in areas where, for example, password reset functionality that relies on a random number generator to create secure or seemingly secure random passwords. You may end up with a reset functionality that creates the same random password for multiple users. And lastly, there's other vulnerabilities that apply to crypto. A big one as of late has been padding oracles. We have a breakdown on our blog of a padding oracle vulnerability. The padding oracle attacks on the blog, and this kind of exploits the padding, various things that have to do with padding when you're actually decrypting ciphertext. Another one is MD5 and SHA-1 length extension, as well as anytime you have stream ciphers or you have AES in counter mode and you reuse key or knots. And just to wrap up some further reading, I highly recommend the Web Application Hacker's Handbook. A new one that just came out is the Tangled Web, and explores the last 2 decades of browser security and kind of the state at where we're at today.